It was where we had ti, ti plus 1 equals some ti. And we took a union with that and some edge ei plus 1. Which is fine, except that we had already defined some sort of t star previously. And it turns out that ei plus 1, that element, is not in t star. So we have this goal that things that are promising, that we're building towards some sort of t star, and it turns out that we've just added an edge that's not in t star. So that's this like the central conflict of the story, of the narrative that we're building. Do you guys want me to throw up the notation from last time, or should I just skip forward into the subcase? How do you guys feel? Okay. Done. All right. So really, it centers around the idea that we consider this u and v, this specific edge. Consider u, v, such that it characterizes ei plus 1, or edge I plus 1 is uv, is that set. And we also know, so we know that that u is within our ti, and v, our v is not in our ti. Sorry. Yeah. So we also know that u and v are in t star, because t star connects to every node. Every vertex is connected through some path in our minimum spanning tree. So it turns out that ei plus 1 and the i's of t star is a bit redundant. So that's where we get the conflict with the cycle. So that makes sense. So last time I gave you guys a definition, it was a bit clunky. I'd like to rectify that with you. So last time I gave you guys this x, I'll make it really big. That is in t star, right? And I briefly mentioned in passing, although I hadn't written it down, that these ES's, this sequence, is the sequence that connects u and v. And it could be many, like it could be many elements. It could be a long chain. You know, like if you have some graph that looks like this, and this is our ei plus 1, you know, es could be everything here. So it could end up being the whole rest of the graph, right? And so by adding this element, we're creating a massive cycle. So that's why we have to consider the fact that perhaps this set could be very large. And does that make sense so far? We could make a better definition. Like, I mean, we can just specify it a bit better by saying something like es in t. Anyway, I'll leave this one. That's fine because it's sufficient. But we just have to remember that this is what it is. And so now let's consider our x star. And this is where I made a legitimate typo, and I apologize, which probably confused everybody so much, and I feel terrible. I felt terrible for 2 days now. I'm not even kidding. This is the set difference here, not the intersection. So we're going to take this x star to be our set of connecting vertices. right? And if we imagine that we already have some subset, so we've already built this Ti, that really what our Ti, that what this X star is, it's just the elements that are remaining that connect U and V, let's say. Or actually, this would probably make more sense if this was U and this was V. Right? So, all of these guys, so starting here, I'm actually kind of lost track of the number of nodes. All of these guys would be our, if this was a set, this would be our X star. Essentially, it's the elements that are missing to complete the path to V T star's way. Like if we were going to make the optimal set the way T star made, this is the way that we would complete that circuit. Does that make sense? Pause me now if that so far is like confusing. So yeah, previously I had written this, which doesn't actually make any sense. Okay. So, yeah, so I can write it out too. Okay, so X star is all the edges that need to be added to Ti to reach the T star's way. So it's just that if we were gonna be exactly like T star, then we would have to add X star. But instead we've added EI plus 1, and now we have to make a choice of which one of these nodes to get rid of. But T star is optimal, so we're in a situation where we have to choose to get rid of another optimal edge, and so that seems to be a contradiction, that we have to get rid of an optimal edge. So does anybody want to tell me what the next logical sort of how we've saved ourselves from this situation? Because we've kind of got the setup here, it's perfect. We can't create a cycle, we know Kruskal won't do that, so that's already, so we're going to kick out some edge. So how do we avoid this problem? Like what about this problem have we? And it's kind of like the activity selection problem, it's the same idea. So we've done some pre-work that has solved this problem for us. Let me know what that was. Basically, the edges are all sorted by weight. The edges are sorted by weight, so we know for a fact that our weight of I plus 1 is going to be less than or equal to all the weights in ES. And this actually takes us pretty far, right? Because we've gotten to it first and we've added it first, right? So none of these previous edges would have created a cycle if we've been using already, because they come later in T star. So we haven't had this conflict yet. And we also know that just by virtue of the fact that we haven't reached those edges in ES yet, we haven't added them yet, they're the edges that are extra, that are required to create T star, that we're ostensibly we're going to encounter them in the future, that we're fine to, that we've reached EI plus 1 first. So it has to be, at least it has to be equal to these other edges. Like they might all be 1s, for all we know. And so that's the real crux. So if we kind of call this, some sort of fact A leads to a couple consequences. Specifically, we have like A1. So the first consequence is it directly implies that for all the ES's in this sequence, it strongly implies that all the ES's are in the sequence of EJ, j equals I plus 2 to the n. So it implies that the ES's are in the future. Like we're still going to encounter them. So these x's are still going to be considered at some point. Does that make sense? Because we sorted the edges that we're going to bump into them in the future. And then if we think about the other case, or A2, we know that our TI union with our EI plus 1 connects U to V with minimum, or minimum weight. So that's basically everything we need to talk about the fact that we're still promising. So I'm going to put out the definition of promising now. Right? We can do one step further before we get there. Is we can just say that given everything that we know, because we know that we still have a minimum weight that we're adding. So the weight of the graph that we're building is still as small, or technically smaller, given that WEI plus 1 is less than those other S's. We know that we're still building a tree that's small. So we can just say, that we might be, oh, I read it here. Don't get that on my sense. Yeah, no, that's perfect. Okay. So we can add our EI plus 1 to this set T star, and then we can just take out the ES such that it's the ES that connects V. So just take that right out. Right? So let's form that, and let's consider that as a potential optimum set. So do you guys think that is T star star is optimal? Like what would make the set optimal or not? Has to connect all the vertices together. So this does that. It connects all the vertices because we know from above it still connects U with V. Has to be minimum weight. We know that because we've added an edge that's minimum weight. So we can kick out this other edge that conflicts with this later because we know that by definition it has to be bigger or equal to the one we just added.
So T star in definition A is all of the edges in the route, right? So does EI...
it doesn't include the dotted line.
Yes.
Yeah, okay.
So then EI plus 1 has to be less than or equal to every other edge, or just the remaining edges?
Just the remaining.
Okay.
Yeah.
So does that mean remaining when you say ES belonging to T star?
Okay.
Where is this?
In definition A.
That's X star. That's X star.
Oh, I'm sorry. Yeah, you're right. I'm the worst person ever. Okay, there you go. Yes, that's exactly what I mean. So it means that of the edges that are left, yeah. You guys, is that perfect? That makes sense? You're following along? Okay. So that's, I mean, we've kind of set up the language. So now if we consider what promising is, if we consider our original definition for promising, things are they look pretty good. So our main definition for something being promising was that we have this set Ti, and that if we sorry, on the notation. I think we'll just go for it. Let's just go for the final definition. Yeah. Okay. So if we take Ti and we consider this new element that we've added I plus 1, it turns out that that we can trivially say that this is a subset of our T star star. In fact, we've set up T star star's definition to be that way. And that T star star in turn could be a member of this larger set, which is Ti plus 1 union with all the remaining elements to be considered, right? So I'll write out what that looks like in a second. Let's just make it just for simplicity. I plus 2 to m. So in our little toy example, where we had a cycle, we'll draw all these out. So this can be EI plus 1. This can be U and V. All the weights can trivially be 1. So we'll just have unit weight for simplicity. And then, potentially, these double lines can be Ti. So, are in Ti. And then we'll say that it's hard to draw. Maybe I'll draw it as a separate thing. We'll leave this here as floating. And let's now draw a T star. And T star might be something like this. So this one might be T star, right? So all we're doing in this operation is saying, forget this guy, we don't need him, because that's the ES that connects V. And we're going to consider the remainder. And we know that this ES has to be greater. And so we also know that this is in the family of edges that are possibly optimal. So these E's are these guys. They have yet to be considered. So they're also, your ES's are in here, right? And I mean, if there were there could be other edges that have yet to be considered as well, that are not included. But they will be in the set of E's, right? Like, I mean, if we want to add some of which, does that sort of make sense, what we've done? We've just switched our definition of optimal, and it's still going to be a minimum weight spanning tree. Cool? And so this is like a lot to write for a proof. You know, there's a lot of writing and a lot of justification, and it's definitely fine to write that much. But we could come up with a little statement. So this is our definition of promising, and it still holds, which is good. So in every case, the algorithm is optimal, and if you compare back to the previous subcases, it's fine. Yeah. Do you guys feel like that's sufficient? Well, it is sufficient, but there is a sort of statement I can write, like a proof statement, but I kind of want to jump into some other stuff. So if you guys still have problems with this, then we can consider something I think you'd probably be excited about, which is shortest paths, which is fun subject. Cool. Do you guys have any questions though, before I jump into it? I'll just leave that up there for a while. So, like I said last time, we're going to consider a connected graph, or we're going to consider a graph, G. So consider a graph. And we have a start vertex and an end vertex. Or terminal, or whatever you want to, however you want to talk about it. And so the goal, broadly speaking, is to find the subset of edges that minimizes some sort of function, and also gets us from start to terminal, from start to end. So specifically, we're interested in some P. P that's in the set of, that's a subset of the set of edges, where for all the edges in P, cool. And so it's not always obvious. It's not always the least number of nodes. Like you can draw a trivial example pretty quickly. Given a graph like this, where this is maybe 7, 5, 10, where the shortest path might be something like, say this is start and terminal, or something like that. So the question is, how do we find that? Does anybody have a suggestion of an algorithm?
Combine search math,
Yeah.
uniform cross search,
Say what?
uniform cross search.
There's a bunch. There are so many approaches. We're gonna consider Dijkstra's.
Yeah,
Yeah.
it's pretty simple.
Yeah. I mean, most of them are some permutation or some combination of either Kruskal's or Prim's. And Dijkstra's is basically based on Prim's. You're just gonna explore the graph, and then given every point you arrive at, you're going to you're gonna just keep a sort of tally of the distances so far, and when you're done connecting the start and finish node from the possible directions, you're gonna make sure to keep your sort of shortest paths updated and a sort of a trace back of the shortest path to get to that point. So, just gonna throw up an algorithm. I'm gonna kill this board. Do you guys need this? Okay, or maybe this one. And then we're going to talk about, we're not really going to do an example, we're just going to talk about quickly how we might approach proving whether or not it works. So in this algorithm, we're going to have a path that we're going to initialize and a queue that we're going to initialize. And this guy is going to be our sort of list of edges that we're going to keep track of. And this queue is going to be we can use a priority queue. Write that nicely. Of edges. Of vertices. That's weird. Should be vertices. This is what I wrote, but I feel like it's... So, yeah, it should be, anyway. So we're going to initialize our queue. And the general idea is that we're going to set B. So this pi is going to be our traceback. Be nil, nothing. And we're going to set the distance so far to the node to be infinity. And so these are basically arrays. Oops. Distance, oh yeah, last one. Node. And this is the shortest distance so far. And then we take our start node and we just set up the idea that the start node is that we're on it. So if you want to tell me, I feel like my notes are lying to me. Do we track, in Dirkstra's, do we track edges or nodes in the priority queue? I wrote edges. Well, we'll see where because I have been known to run around with my notation during lecture.
It matters.
Yeah, like it doesn't technically.
Yeah.
Yeah, because you're going to go for each, no, you do push edges. So let's think about it for a second. In Dirkstra's, you're going to push edges. And the edges are stored in a priority queue such that when you get to each node, you want to access that list of.
Right. The one that you just wait.
Yeah. So it's going to be, okay, yeah, so that's fine. Okay, perfect. Okay, so then we enter our main loop. So the main loop, and here, where do we do that? And here, before we get into the function, sorry if you wrote that close, we have to enqueue. We have to enqueue all of these in queues, which is why I feel like we're actually tracking what we're doing. But we'll see in a second when we dig into the algorithm. So in our main loop, the general idea is that we just say while the queue is not empty, we're going to grab some element u as the, and this is the textbook's sort of take on it. So it's the next element up according to the priority queue. I'm going to set P we're just going to add in a pointer to our U, or to the sort of traceback. and our U element. So that's going to be our path tree that we're slowly building. So do you guys understand what pi is? Pi is going to be our tree at the end of the day. So pi will end up describing, given a node, S, all the pi values, say this is t, the pi's describe this sort of structure. So these are, all of these guys are pi's. So it's just saying each one has a pointer to the predecessor that is the closest. And so the general idea with Dijkstra's is that as you explore the graph, that you continually keep updating these pi's such that they're minimal. And they start out as infinite, and so you greedily do that update. Yeah. So you pull an element from Q, you pop it into your set of your things considered in your path, with the idea that you have this pointer that you might change later. And then, yeah, so that you do deal with the edges, because for each vertex V connected, or for each vertex V, UV, we just want to perform this relaxation function. Has anybody seen this before? Is this like super familiar? Have you seen the relax, the idea of relax before? No? Okay. Sometimes I'm not sure what formulas or algorithms you guys have been exposed to previously. So I'm not necessarily sure. So if I do something that's completely foreign, just stop me and I can explain in more detail. If I'm doing something that's very redundant, just let me know and I can skip ahead. So let's define this relax function, because this is kind of the core crux of the algorithm. Or, well, definition, I should say. Definition and also direction. So in relax, all we do is, so we just say if V is in Q. So if V has yet to be visited, if it's a node that's coming up, and if the current distance that we have to U plus our weight function, which is less than the current distance we have to V, then we want to relax these values. So I'll explain what that is in more detail in a second. So we update the predecessor of V to U. And we also update our distance to be du. So does anybody have an inkling of what this means? And we can also, just as an aside, update our queue. sense what we're doing here at all? Or is it totally weird? So I'll give you guys an example. So the general idea is that we have some the general idea is that if we have these, this is a very trivial example. So this is a 5. That at iteration 0, the algorithm will consider these as infinitely far away, and the distance of this guy is 0, as it should. All right, so this is a 0, that's infinity, infinity. Right away, the first thing the algorithm does is it's going to assign this a distance of 1, and assign this a distance of 5. Right? Now, since we've sorted things greedily, the next thing we're going to do is consider this node. And so, after moving here, we're going to pop this. So this becomes the first entry in P. So P now has S. Then we're going to jump into U. And then it turns out that this is a candidate for relaxation because there exists a V such that the distance to U plus, the distance du plus the WUV is less than our previous, this is dV, right? So then we want to relax that amount. So we want to set dV, or the predecessor of pi. So we want to, instead of the predecessor being this guy, like that, we want to change this and make the predecessor instead here. And then we want to update this distance here to be, the distance of dV to be the sum of the distance to U. So we have that pre-baked value here, right? We don't have to sum it over the whole path. And then we just want to add that here, so we end up with 2. Does that make sense? Now that I've kind of worked a little baby example. I thought I had worked one, but I had to make one up. There's a really good example in the textbook on page, where did I put it down here? Page 659. So check out page 659. And it's a good exercise just to work through Dirkscher's algorithm step by step. It can teach you a lot. And it's a pretty clever algorithm. It doesn't necessarily seem intuitive, but what's the time like?
9 minutes.
Okay, great, perfect. So, I mean, let's start thinking about correctness. So, Dirkscher's an interesting example. I looked online for ways that people prove Dirkscher's is correct, and there are a lot of ways that people have used to prove this algorithm is correct. Can you guys think of any candidates? I mean, what's the standard approach we've been using so far?
Promising.
Sorry?
Showing that each step we take, we still have a promising candidate.
That's exactly it. So that's one approach. So one approach is to say that, as we're building this tree, that it's always promising. So in order to show that something's promising, what do you have to establish? So in terms of correctness, let's talk about it. I'm just going to throw you guys out some tools. So one approach is the promising approach. And you can say that Dirkscher's algorithm is greedy. So the real characteristic of any promising approach, if you're going to consider induction, is that the locally optimal choice is somehow optimal. And you can do that by building a history. So you can consider your PI, P2, or P1, sorry, P2, PI, PN, and then you can also consider the characteristic of some optimal set. And you can show that through the operation of the algorithm, you don't ruin your chances of reaching that set. So you need to find a definition or a way to characterize promising. If that makes sense. Turns out that's one approach. Dirkshire is interesting because it doesn't only have to be seen as a purely greedy algorithm. It can also be seen as an algorithm that handles subtrees and subproblems and optimizes them. And so that's why people like to talk about Dijkstra's, because it's kind of like a natural next step to the idea of having optimal subproblems. And what Dijkstra's really doing is that you start out with these massive distances. So if you think about it sort of another way, in Dijkstra's you start out with weights for nodes or values for nodes that are infinity. And you slowly try to relax the graph and tease the issues of the graph until eventually they converge. And so really what you want to do is there's more tools as well that you can consider. There's the idea that this relax function, maybe it functions such that it decreases weights, but never below some sort of optimum value. So what can we call these optimum values if we want to talk about them? We just make up a function. So, I mean, in the literature, they typically talk about these as delta functions. So, such that So to do that, I feel like I don't have my watch. How are we doing? 5 minutes? 4 minutes? Cool. Okay, so I'm just going to quickly define delta functions and get you guys thinking about the topology of delta function versus the topology of the network. Really quickly. And we're just going to get the notes. So it turns out that if you have a graph, broadly speaking, that these can have all kinds of crazy weights. You can have like a 10, a 7, a 4, a 2, 1, whatever. But it turns out that if you take that graph with these really unpredictable node values, so these are unpredictable. Sorry, I'll call them crazy. You can't forecast them. It's a really hard problem to solve. But it turns out that if you just formulate the idea of a shortest path from U to V for any U and V, and you just define that as the shortest path. So let's pretend that to get from node 1 to node 2 or whatever, that you could go through many, many subnodes. You know? So this is a U, a V, a Y. Do you have any idea like what you can exploit in this situation? That's really useful whenever you have 3 things.
Triangle inequality?
Triangle inequality, yeah. So it turns out that in these situations you have access to triangle inequality. Oh yeah, I remember that. So the idea is that you know that there exists one shortest path here, one shortest path here. So there are shortest paths between U, V, and Y. And what you want is your algorithm to converge on those values. And so broadly speaking, the solutions are going to have the proofs to prove the correctness are going to have 2 sort of camps. And I'd like you guys to think about what these camps look like. But the first is the greedy approach that we've currently been talking about, where you build a set. And the other is that given exposure to some subset of these, so say we define these, broadly speaking, as, this is PI and this is, another subset, that you can prove that Dijkstra is finding an optimal solution for this subproblem. That the values, so if you consider, a really tiny subgraph of 2 items, does Dijkstra find the optimal shortest path for those and obey the delta functions, considering the service function, like the relaxed function it's using. And then if Dijkstra is gonna add to that problem, is it going to continually? And this is where we get into the idea of starting to roll into dynamic programming, where we consider problems as the complete problem can be recursively broken down into smaller problems, and you can form your solutions that way. And so that's where we're going to be going next. Yeah. So that's the Reader's Digest version of the sort of things where we're going to. Do you guys have any questions? Or? I guess you're here for a tutorial, right? So we can keep talking. Yeah, we scheduled it in here. There are like official rooms, but I figured that it would be good to have you guys here. Do you guys have any questions about the assignment? No? Oh, sorry, I didn't even. So I had a little surprise for you guys as well. Yeah, no, come on up. So this is Johannes. I work in a cool space with lots of talented individuals, and I kind of have the opportunity to sometimes invite some of them to talk about stuff. So I wanted Johannes to talk a little bit about greedy algorithms in the wild if he wanted to. But yeah. So yeah, talk a little bit about yourself. So do you want to plug
No, I'll do this.
Okay, cool.
Say that.
Okay, sweet.
So yeah, I'm an electronic engineer and a computer scientist. I spend approximately half my life working either in the real world or in the academic space. Both are much the same. I generally try to pitch myself as the bridge between the worlds. So I like companies that are closely related to universities because there's a lot of new interesting ideas coming up there. But I also like companies because there's a lot of reality attached to companies, which sometimes some people might say slip through the university experience. So, Dijkstra, who's suspicious that they will ever have to use this in the real world? Thank you, one honest person. So it turns out that it's. I do, but that's mostly for me. That's a short.
Oh.
It's fine. So yes, I'm going to spend 5-10 minutes and quickly take you through distributed systems, which are a big thing of mine. Looking at algorithmic complexity, specifically looking towards communications complexity, because that is something which comes up a lot. Using the example of a network of satellites, because space is sexy and we need to sex up computer science. As I said, this is very much an engineering perspective. So the main takeaway I want you to have from this is one, that the big O matters, and computational complexity maps very well into a lot of other problem spaces that you encounter. So when building a system, we frequently end up going, here's a problem that we need to solve, and there's a set of functions that we can use to solve this problem. The complexity cost, which frequently translates to the real costs of all of these possible solutions, are a function of, as you've seen, computation, definitely, like the number of CPU cycles that goes into solving a problem. That being said, in today's world of relatively fast CPUs, a lot of people care less about that. That's why the internet sucks nowadays. Another thing is memory. Different algorithms will use different amounts of memory, and yeah, this definitely has an impact, especially when moving towards things like mobile devices. The other thing about mobile devices is, depending on which algorithm that you execute on them, your battery life is going to go way down if you choose a bad one. So these things are very real. If you're looking at networks and multiple units that have to interact, bandwidth comes in quite a lot as well. And that's where a lot of today is going to go into. So when implementing systems, you will be trading off all of these various parameters: memory, computation, communication, and a lot of it, for me personally, my day-to-day working life maps to battery life. So there's a very formal way of going about communications complexity. You can look at that. This guy called Yao in 1979, he wrote the first paper on that. Exciting stuff. I'm going to be nice and high level and hand wavy because that is more fun for me. Looking at distributed systems, we broadly can consider them as a set of computers or computing nodes that are connected in some way. Examples of these, like the exciting ones at least, would be things like deploying teams of robots into disaster areas, like, post-earthquake spaces, which is quite dangerous for your first responders, which is highly unpredictable and unmapped because the physical topology has changed. Dangerous spaces where we want to send basically disposable technological solutions into to make our lives as humans safer, better, and hopefully happier. That's one. Wireless sensor networks, where you embed a large number of low-power sensor nodes into the environment to measure things like water temperature. I know I had a friend who was working on a system detecting mudslides in Mexico using exactly this type of thing. Small amounts of computation, very little communication, but by keeping costs low, you can have a very large system and a very large sensing footprint, which then allows us to make decisions and detect things happening. In the Google and Amazon space, data centers. If you have a farm full of computers with applications running on them, and you need to shift those virtual computers onto other computing farms, how do you balance that load? How do you transfer that data? How does it all fit together? What's the best strategy there? And my personal favorite, there's a research theme going on looking to see whether we can, instead of building one large big satellite that costs billions of dollars, takes 15 years to build, then we launch it and we lose it on launch. Instead of that, can we get away with using a larger number of small satellites that collaborate to solve problems? So you effectively spread the functionality of the single satellite over a bunch of smaller ones. All of these systems are dynamic, so nodes fail, things break, they all change state independently due to the environment, due to work that they're doing. For many of them, communication has a finite limit. You can't just push an infinite amount of data from one point to another, even if you're working between data centers like Google and Amazon. And generally, as system designers, we want to maximize the global system performance of all of these. So a lot of the algorithmic things, like the proofs you were doing on Blackstar just now, if you can solve things locally, can you scale them to a large thing? That is a very big question in research on exactly these systems, and it maps over frequently into the real world as well. So, imagine that as a number of satellites. As they move around the Earth, when they get close enough to each other to communicate, links are established, and we can have communication. But as a result, the entire network topology is changing constantly. This one might be taking photos, this one might be communicating the photos down to the earth. When they get together, they can do that. But if you're further away, you may have to relay your data going on. So it's a very dynamic problem space. It shows a lot of the problems we see in other networks, from Wi-Fi all the way through to the global internet. A lot of them come out here. So, as an example, suppose this node tells this node to take a photo. To do that, we need to communicate from here to there. That's one problem, and we all know how to solve that, and hopefully we can prove how to solve it as well. But there's another problem. This node needs to know what the network looks like. And that's where it starts getting a lot of fun. So, this one needs to build a network model. In other words, map the graph, including the state of the individual nodes and the links and the link weights between them. Then using that abstracted model, we can use any one of our favorite algorithms to find the shortest path and route our data through. However, this requires communication. So much the same as we were optimizing computation over here. Now let's see what we can do let's look at the impact there. So if we were to measure this multiple times, we can show that the communication complexity, in other words, the number of packets we need to send across the entire network for one node to have an image, a good model of the network, is approximately n squared. Slightly lower, it depends very, very much on your network topology. So if you know your network topology, if you know things about your network topology, you can frequently lower this value. If you don't know it, that's where you're going to be. Crucially, if your network is constantly changing, the time to measure and capture the network state also needs to be faster than the rate of change. Otherwise, we end up with outdated models. And they are sometimes vaguely useful, frequently quite useless. Alternatively, if we have perfect knowledge about what's going on in the system, we can model it. So this one knows approximately where that one was at some point and can map forwards into the future. This drastically lowers the communication cost. However, it does push up the processing and memory cost on this node. So again, we're working on this trade-off. Do we want to communicate more? Do we want to compute more? And for every system, the sweet spot will be somewhere else. That's why I still have a job. In reality, you frequently end up with a hybrid model. You do this from time to time, depending on the rate of change in the network. And in between those updates, you model. And you model. And every time you get new data, you correct your model. So there's some prediction going on and some measurement. And that allows us to steer a good course. Again, finding that sweet spot, that's what we get paid for. So the real internet does not have that communication complexity. So it turns out there's a good family of alternative protocols where you can get that down to, depending on what the type of problem is, down to linear complexity, or for some specific subsets, even constant complexity. So you're independent from the network size, but it has an impact on the computational complexity of the algorithms. So frequently you'll be doing local optimization, greedily optimizing and mapping a small part of the network and breaking it down into a hierarchy that you can push things through to get it done. I'm not going to go into the details of that. So if we now have if that's the communication complexity, this is the number of nodes in the network. For the first protocol we suggested, we see our normal happy n squared situation there. The constant communication cost thing sounds amazing, but it's also important to keep in mind that many networks will fall into this space, where over here I would say, yes, use that by all means. When you exceed a certain number, and that number is frequently, for the systems I looked at, between 50 and 100 nodes. Again, other people have come across I think, pushed that up to a few thousand nodes, depending on the network infrastructure. The type of solution that you want to use is going to depend on the space. So that's what my life is like, I think. The short answer is, it depends. It depends on a lot of things. Crucially, it depends on being able to estimate the complexity. If you can't estimate it, you can frequently measure it. You can see, we can build models to see how things change and map that into a function in working a lot of stats. Questions?
Cool. So just as a just to give them a sort of what was your research area?
So my research focused on exactly this multi-satellite problem. If you have a bunch of satellites and you need to maximize the return on investment, because we're talking about millions of dollars, which mostly maps into the number of kilograms that we launch into space. How do we maximize the return of photos per kilogram, which can be translated to photos per original dollar spent? So the question is, given one of these networks, what types of protocols and management structures should we come up with, and can we safely use to make these usable? If you're talking about 10, 15, 20, 100 nodes, we definitely have a lot of techniques to cope with those. If you're looking at more than that, 500,000 in highly dynamic networks, then suddenly a lot of the proven technologies we have, the protocols we've developed for terrestrial, more stable networks just don't fly. So my focus was very much on driving protocols and looking at how to allocate tasks, so who does what in one of these systems, in such a way as to maximize the system lifetime and, by implication, maximize the return on investment. That was mostly CS, but some Astro. Yes.
So when you're working with distributed systems, what programming languages do you use? Do you use Python or Erlang?
It depends. All my answers will start with it depends. For me, as a fairly low-level embedded engineer, frequently I will do my modeling in Python, implementation in C, something like that. Looking at a higher level, more data center type things, definitely Erlang, Hadoop, the standard Googly languages, they definitely come through. If you are using them in an application, definitely the high level languages. If you're building the infrastructure for other people to put an application on top, you will look at the language languages. Personally, I'm a great fan of using lightweight, high-level, powerful language, i.e. Python, to test ideas, verify, get some stats before going to the effort of getting things working on hardware. Because that takes forever, usually.
I'm just curious, when you were, as you probably did schooling for engineering and for computer science, in your opinion, what was the thing that you said, man, I am never going to use this as an application, and then lo and behold, when you actually got into the real world, you definitely used it?
So let's see, in the last week, electromechanics, this stuff's impossible, but it has come back. Some formal verification. Exactly this type of system, it turns out that the space industry is extremely conservative. Extremely. They make libraries seem vastly progressive and exciting. Those two definitely up there. I thought I would only ever write one compiler in my life. Turns out I constantly pass and process data, which is basically compiler theory, but just applied to various problems. This group of grammars, they've come back. Yes, those are, I think, the main CS ones. Mechanical engineering subjects, the first year ones that you go through, to make you a well-rounded engineer. All of those have come back. They're more like product life cycle as well. Basically, there's a reason most of these things are put on your path by wise old bearded men. And soon women too, hopefully. They don't have to.
Anything, yeah? So yeah, if you ever want to talk about satellite theory or any of the embedded programming, I can definitely connect you with Johannes.
Yeah.